Okay. Let's see, an announcement. Course evaluations will be coming up pretty soon. So I got an email this morning saying that you should be getting an email in the next week, I guess, with directions on how to do a course evaluation. Those are due on, I think, May 3rd or something like that. You'll get an email though. So please do that. It helps to make the classes good. What I was going to do today is work through the conscript and just see in more detail the application of some of these predictive methods with the con data. And then if we have time, we'll start talking about our final topic, which will be proteomics. So anytime there's an omics at the end of a word, that means we're like genomics, proteomics, metabolomics. We are characterizing the total collection of genes in genomics or proteins in proteomics. So proteomics is a little bit different from things that we've seen, but it does have similarities. There was some interest on the discussion board in talking about some of the common statistical tasks that are involved with proteomics, in particular mass spectrometry based proteomics, which is a widely used platform for doing this. All right, so if we have time, we'll start on this. Otherwise, we'll start on it Wednesday. Meanwhile, here's the con data. So let's do some statistical learning with the con data. Okay. So setting aside 2/3 for training and the rest for testing leaves us with 54 training samples and 29 test samples. Each of these data frames, here's the first 5 rows and first 5 columns. Each data frame has all the 2308 genes in the columns, but the first column contains class membership. All right, naive Bayes was one method that we met. This is essentially assume a normal distribution for all the genes. Assume that all the genes are importantly independent, statistically independent. So there is no correlation between the genes. Almost certainly, an unrealistic assumption. But as I've mentioned, sometimes making overly simplistic assumptions can result in decent performance, especially when we have lots and lots of variables and relatively few replicates or samples. All right, so naive Bayes gives me that's not very helpful. The main thing I want out of naive Bayes is predictions. So this model, or having done that, basically fit the model to the training data. So we estimated all the parameters of the model, which basically means we estimated the mean for each of the genes specific to each of the classes. Each class, we now have like a vector centroid means of the 2308 genes that is typical of that class. So we've computed those averages, and we've also computed some standard deviations for each of the genes. Then prediction is pass in your new data for each of the testing observations. Take all 2308 numbers for an individual and ask, in a vector sense, which centroid is that closest to. Compute a distance between those 2308 numbers and the separate centroids for the different classes, and classify to the group to which it's nearest. The truth for that individual is 2, class 2. If we do predict, we can check how we did. So here's the first 5 predictions. First individual, we correctly classified as a 2. Fifth individual, we got incorrect, though. So the first 4, we got all correct. The last one, or the fifth one, made a misclassification. This is what we've called a confusion matrix. If you cross-tabulate your predictions with the truth, then you see all your errors. How accurate overall speaks to sum of the diagonal divided by the total number of test samples. But then, more specifically, we can say for class 1, we're excellent. We always got that one right. Class 2, not quite as good. Class 3, a little bit better. Class 4, we did great. It may be, for example, you have 4 different tumor classes that you want to discriminate between. Do you have prostate cancer with Gleason score 3, 4, or 5? It may be that 5 is easier to distinguish. 5 is extreme, and your genetics have gone haywire. So we may be able to very accurately say whether you are class 5 or not. But class 3 versus 4 may be harder to distinguish. That's why it's nice to look at a confusion matrix rather than only looking at the misclassification error rate, because now we can say things that are specific to the classes. This method does a really good job of predicting, if you have like a life-threatening situation, but when it comes to some more subtle distinctions, are you this class or that class, maybe we don't do as well. This would then be the misclassification rate, so just the total number of errors divided by the total number of test observations. Overall, 86% accurate. Okay, here's k nearest neighbors. And we went through for a collection of values for k. K nearest neighbors means for each of our individuals to be classified, we take the vector of expression values, or whatever we're measuring, and we find, in a vector sense, the k individuals in the training set that are closest to that individual. So back here, we would take those 2,308 numbers, and for that individual, we could compute a distance between that individual and all the training observations. And whatever we've chosen k to be, pick the k that have the smallest distance, and for those k individuals, the nearest neighbors, their training data, so you know the truth, you know the class membership. So say we did k equal to 5, we'd go find the 5 nearest training samples to this row, and some of them are class, like maybe 3 of them are class 2 and 2 of them are class 3. Then we would predict class 2. We would take a majority vote. Find the nearest neighbors and take a majority vote of their class memberships. With KNN, with every one of these methods that we have met, there's some aspect of it that needs to be, quote, tuned. In KNN, we need to choose K. In naive Bayes and linear discriminant analysis and quadratic discriminant analysis, we have to choose the threshold above which an estimated probability of being in a class is turned into a prediction of that class. Lasso, we have to tune that shrinkage parameter. Random forests, we have to tune the pruning of the tree, stuff like that. So for K and N, we needed to tune, and one way to do that is to try a variety of K values, compute either a test accuracy or a cross-validation based accuracy for each one, and then make a picture. So look at the picture, and hopefully there's a clear winner, as in K equal to 4 achieves highest accuracy. In this case, there's not a real clear winner. Which of these K values is optimal? There's going to be some variability, so I don't exactly believe every last zig and zag in this picture. If there were multiple values of K that seemed to have the same accuracy, like in this case, K equal to 3, K equal to 4, and K equal to 8, all appear to achieve the same accuracy of about 93%. If I had a choice between these different quantities, it's not clear. Yeah, I don't have like a generalizable recommendation for which one to pick. The principle that I would use in deciding is the bigger K is, the more or the less flexible the model is. In the extreme, if K is equal to the number of individuals in your training sample, then for that row of individuals that we were looking at in the testing, these guys, for this individual, we would compute the K nearest neighbors. But if K is equal to the number of training samples, that's everybody. That's all the training samples. So my classification for this individual and every single other individual would be just the majority vote of the entire training class. So increasing K will decrease the flexibility. What do we know about what that translates to in terms of variability of the method, though? We've talked about mean squared error, that kind of thing, being a combination of bias and variability. Increasing K, do you think that increases or decreases the bias of the method? You would increase the bias because it becomes less flexible. So the less flexible the method, the more likely it is that it's not going to be able to pick up on the subtleties of what the true relationship is. So we're going to get more bias as we increase K. What's going to happen to the variability of the method, though? It'll decrease. So there's always that trade-off. Increase flexibility, you tend to increase bias, but you decrease variability. Go the other way, decrease K. In the extreme, suppose we choose K equal to 1. Then we're going to find just the one training observation that's closest to that row. And whatever that individual's class is, that's what we predict. There is really no majority vote anymore. That's going to be highly flexible, but it's going to come with a lot of variability. If you were to redo that exercise, go get a new training set and some new test data and redo this, the accuracy rates and the estimated parameters of the model would vary a lot. So, having said that, I might not choose the smallest, I might not choose the largest. Let's pick the middle one. I might pick 4 as a compromise between those 3. Lasso is basically a fancy version of linear regression or logistic regression. In the Yeah, so in like the logistic regression case, if we wanted to classify between, say, disease and healthy, we could do logistic regression on disease-healthy status in terms of a linear model of predictor variables, which in our case would be genes or features. So we could have like a log odds of disease equal to regression stuff, beta 0 plus beta 1 times the expression level for gene 1, plus beta 2 times the expression level for gene 2, plus dot, 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 all the way through our thousands of features. That would just be logistic regression, which often does a decent job, but with lots and lots of features and relatively low numbers of replicates, the idea of shrinking, stabilizing, moderating can bring with it real gains. We talked about moderated test statistics, for example, when in the context of next generation sequencing data, which is similar to this. Let's take, instead of using the individual estimates of all those beta coefficients in the model, recognizing that with so many features and such small replicate size, such a small sample size, those estimates are likely to be very highly variable. The idea of the lasso is to shrink those coefficients, shrink the betas towards 0. Big positive betas get shrunken to be smaller, closer to 0. Big negative betas get shrunken towards 0. They get a little bit bigger. And with the nice result, I guess, that the lasso will end up actually selecting out some features. Rather than just shrinking the coefficients to be smaller, suppose we did that. Suppose we had 2,308 genes. We fit a logistic regression model for disease versus not. We have a coefficient for all 2,308 genes. To use that model in practice, like somebody walks in the clinic and you want to predict do they have the disease or not, in order to use our model, you'd have to go assay all 2,308 genes. Like run a full microarray on somebody. It's expensive, time-consuming. So the idea of shrinkage is a more useful diagnostic tool would require a smaller number of features. So it's nice to be able to take my 2,308 genes and not just shrink the coefficients to reduce variability, but shrink them, in some cases, all the way out of the model. So at the end of that, instead of 2,000 genes that you have to assay to make a prediction, maybe you only have to assay 100 or something. So lasso, think regression, except we're going to shrink the coefficients towards 0, and in so doing, we are carrying out feature selection. The lasso functionality in R proceeds by using the cv.glmnet function first to do cross-validation and tune the model. How much should you shrink? A little bit or a lot? In one extreme, you don't shrink at all. In another extreme, you shrink every single feature out of the model. Where should you put that tuning parameter in terms of performance, classification performance? So cv.glmnet thankfully makes the job easy for us and does cross-validation automatically. Then we can make an informed decision about the tuning parameter by looking at a picture like this one. Which value of the tuning parameter achieves the lowest misclassification error rate? And here again, if I had ties like we do here, there's a whole range of lambda values, that's the tuning parameter, that correspond to 100% accuracy according to cross-validation. Okay, so so this is actually the log of lambda. The bigger lambda is, the more shrinkage you do. So the more shrinkage you do, the fewer the features you get that remain in your model. So in this picture, I would be interested in maybe not picking a lambda that gives me 100% accuracy if I can increase lambda a little bit and select out a lot of the features. So suppose that, using all 2,000 features, you can have 100% accuracy according to cross-validation. But by increasing lambda, maybe we shrink out a bunch of the features and we're left with just, 500 or something. And the error rate is only minimally different from 0. So it might be that that increase in error is worth the convenience and the practicality of having, a more usable classifier. This is the kind of picture that you would talk about with your collaborator. This is what the data say. You can have perfect classification if you use all the features. If you shrink, or if you do feature selection, we can have a more informative subset and still do pretty well. So where would you like to draw the line? Depending on the context, the collaborator may or may not be interested in feature selection in and of itself. Contexts where feature selection is specifically of interest is where, in addition to making predictions, you would like to learn from the model about what drives those predictions. If there's 2,000 genes in the model, it's hard to say. I have 2,000 beta coefficients. If there's only 100 genes in the model, then it's relatively simpler to investigate those 100 genes further and kind of comprehend what their beta coefficients mean. This gene, as it goes up, increases the likelihood of disease, holding all the other genes constant, for example, while that one decreases the chances, holding everything else constant. Feature selection makes it more likely that you'll be able to see those types of interpretive results. CV.glmnet gave us cross-validation based estimates of misclassification rate for a variety of lambda values. We looked at the picture and we could decide, based on, say, talking with a collaborator, like I was saying, where to pick lambda. One thing that comes out of the CV.glmnet function, though, so names CV lasso, that lambda entry is the grid of possible lambda values that were considered in the cross-validation. So for every entry in lambda, a separate cross-validation was run to estimate the misclassification rate. And over here, lambda.min is the lambda that resulted in the lowest. So CV lasso $lambda min 0.047. If I just wanted to go with accuracy, that would be the tuning parameter I would use. I've tuned my model. Let's use lambda equal 0.047. In order to actually make this into a classifier, though, we need to fit the model to all of the training data. Tuning, think cross-validation for the purposes of just picking the parameters of the model. Once you've done that, though, you should use all of your training data to build the model. And then that would be what you publish. Use my R code to run your test observation through, and it will apply the model that I fit to all my training data and make a prediction. So I need the model that corresponds to that optimal lambda. The way I know how to do it, glmnet is the function for fitting a model. but as far as I can tell, you have to give it a you have to give it a collection of possible lambdas. You can then pick out, and it will give you the fitted model for every one of those. Then you can pick out the one you want. So what I did here is store the lambdas that cv.glmnet picked. That collection includes that lambda minimum that we saw. So fit a separate lasso model for every single one of them. And then down below, we'll pull out the coefficients for the one that we really want. So let's do this. Here's the picture that shows us what lasso is doing. We have 2,308 beta coefficients in a regression model. Log odds of being in a particular disease class equals beta 0 plus beta 1 times gene 1 plus beta 2 times gene 2 plus ... And what these pictures show is as you increase the shrinkage, this green line, for example, corresponds to the beta coefficients for a gene, one of the 2,308 genes. And you can see that as we shrink harder and harder, it gets pulled closer and closer to 0. And at some point, it goes away. So if we looked really close there, that green line went to 0 and is no longer in the model if we shrink this much. All right, so let's pick out the model that we want. Lambda min, pull that out from the CV results. That's that 0.047 we saw. Okay, and then, okay, so if we do coefficients, if we ask for the coefficients of the fitted object, let me just store this in a temporary variable. What we get is a list. So a list, here's the first 5 elements. Didn't want to do that. One, two, three, four. Okay, so we have this is a little bit different from logistic regression. Logistic regression, cancer versus normal. 1, 0, it's binary. You fit a model, you have a beta 0, a beta 1, ... We actually have 4 classes, so logistic regression in vanilla form does not apply. But there's a generalization of logistic regression that is applicable to more than 2 classes. If it's not 0, 1, but 0, 1, 2, 3, you can get what you get is a separate fitted model for each class. So we have separate coefficients for each of these classes. For class 1, we have a matrix. Let's see what that looks like. They just say zeros and dots? Okay. So we've got...
Maybe turn that into a vector instead of zeros.
We have 2309 by 99. We considered 99 separate lambda values. So each column of what's inside this element of the list is beta coefficients for the model corresponding to that choice of lambda. If it works for you to just specify 1, then that's fine. When I ran this originally, which was a while back, I think at the time you couldn't do that, so they may have fixed that. That would be handy.
Yeah, well, when I did it, you can just put random in and it'll run it with just the 1.
Okay.
Or,
That would be easier. So,
put, CV box, so, yeah, it should.
okay, let's see what that does for us.
Then, so if you say bit lasso and $ beta, it should just give you coefficients.
Hmm?
But that doesn't have to be, well, maybe it does, but yeah.
Okay, it looks like it's also a list. It's a list, length. It's going to have a separate entry for all 4 classes. So if I wanted to see the coefficients that speak to distinguishing class 1 from the rest, I could look at fit lasso beta, give me the first element, because that speaks to class 1. It's a matrix. Okay, now there's only 1 column, and so let's do coefficients for class 1 are as.numeric. Let's just turn everything into numbers. Temp. Okay, so now we have beta coefficients, and we have selected out some of the features. There's only 34 features that are left that are being used for class 1. With this multinomial application with 4 classes, we would need to go through and do this for all 4 of the classes. In your homework, with only 2 classes, it was more straightforward. You could just look at these coefficients, which of them are not 0, those are the genes you selected. So your final model, your classifier, would not even have those genes in it. Your classifier would say, assay these 34 genes, plug them into my R code. DF. Let's see. Good. So DF, just as a reminder, our help file always starts with a description, usage that shows you all the arguments, details on the arguments, and then some more detail, and then there's value, which tells you all the stuff that comes back to you. So if I wanted to know what DF means, I would look it up here. So yeah, that's exactly what we want. Number of non-zero coefficients for each value of lambda.
So if you have the like more different sets, you have to like cross compare them and only pick the ones that match up, or how do you do that?
In like in
Or technically, is there 3? It was ABC.
that's right, ABC. So yeah, ideally you would come through here. The DF would be fine. It would do this anyway, I think. But I would come through and I would say for class 1, how many were non-zero. For class 2, how many were non-zero in 3 or 4. How many overall across all of those were necessary. So it may be that like these 5 were required for the class 1, a totally different 5 were required for class 2. All 10 of those were required for class 3, and so on. So in terms of how many features are required for my model, I would add up the unique elements, the unique features that were involved in any of the classes. Because in order to implement the model, you would need all of those. You would need assays of all of those features.
I'm just asking, because for E, you have to actually pull those genes out, classify them. So you would have to go through and find all the uniques across all 3.
Ideally, you would find all of them that show up at least once
Yeah.
for one of the classes.
So you wouldn't be able to just use beta 1. You would have to look at all. Like,
For gene 1, was gene 1 selected, would be go look at the beta coefficient for class 1, 2, 3, and 4. And if any of those are not 0, it was selected. So what I did here was get the coefficients for class 1 and get the row that corresponds to lambda min. And then I'm going to tack together the 4 sets of coefficients . So this is now 2,308 rows, 4 columns. And if I look across a single row, it's the first 6 rows, I'm looking for rows for which there's at least one non-zero coefficient. Gene 1 was selected, the rest of those were selected out, filtered out. But there may be features that have non-zero coefficients for one class, but 0 coefficients for another. It's possible that, say, a biomarker is useful for distinguishing between stage 4 breast cancer and stage 3 breast cancer, but it says nothing about stages 1, 2, and 3 compared to each other. These selected features are genes 1, 107, 123, and so on. So that would be interesting to show to the collaborator. These are the genes. We could go look these up like we did earlier in the semester. Go Google the BRCA1 gene and the Mike gene and so on, the genes that were picked out. Okay, let's look at the feature selection bit here for k nearest neighbors. This is similar to what you did with using t-tests to pick features for naive Bayes. We're going to do feature selection with a different technique, k nearest neighbors. A little bit complicated with the con data because there's not equal numbers of training samples in the different classes. There's fewer class 1s than class 2, for example, and they don't break down evenly into 5 folds. So I made up these numbers in an effort to as much as possible, evenly distribute the training samples across cross-validation folds, 5-fold cross-validation. I randomly picked those numbers of representatives of the different classes to go into the cross-validations, as opposed to just picking the first 5 and then the next 5 and putting them in that way. Randomization is always your friend for minimizing chances of bias. This is preparing to extract or preparing the data to be worked with in the cross-validation folds. I'll run all of that. So fold samples is a list first, and it's got 5 elements. So 5-fold cross-validation. In iteration 1, in the first fold, take those individuals as your training data. And whatever's left, so number 2 is not in there, for example, and so on, will be your testing data for that CV fold. Then these are what you use in the second one, third, fourth, fifth. For each time, like fold 1, you pick those individuals to be temporarily your training data. Everybody else is held out as testing data. We would fit the k-nearest neighbors model for a candidate choice of k, turn around and apply it to the temporarily held out individuals and get an accuracy estimate. I would do the same thing here in the second fold, and then the same thing in the third fold, fourth fold, fifth fold. So for a particular choice of k, I would have 5 estimates of accuracy. And with cross-validation, when we average those 5 estimates, we kind of magically get an estimate of the generalizable accuracy, the accuracy we really care about. How would you do feature selection generally? Generally, you want to pick the features that are informative for discriminating. That's the goal. What does it mean for a feature or a gene, say, to be informative for discrimination purposes? Suppose we're talking cancer versus normal. Gene X has the same average and the same standard deviation whether you have cancer or not, say. It's not affected by cancer. Gene Y is overexpressed in cancer. So its mean is bigger than the normal mean. Gene X, since it doesn't differ, is not informative. It's not going to tell us anything about whether somebody has cancer or not. But gene Y may, because it actually varies. Variation brings with it information. The more, if you want to learn about a quantity, measure it, measure aspects of it that vary enough to paint a picture of the operating characteristics. Variability, like with principal components, we were looking for linear combinations of our variables that were most informative. And by informative, we meant biggest variance. Find the linear combinations of variables that are most variable. In the feature selection application, we'd like to go gene by gene and score it based on discriminatory information. Are you useful for discrimination or not? With 4 classes, like we have with the con data, we could think about for a gene, gene X, here's class 1, 2, 3, 4. Gene X, if we did, say, side-by-side box plots by class, maybe it looks something like this. To the extent that those boxes differ, basically, this is an informative gene. And think about Anova. Anova, we're interested in comparing the mean across 3 or more categories. Anova would give us a p-value that's driven by a comparison of how different the averages of the classes are from each other. So like that's not different from that one. but there's a difference there and there's a difference there. So there is some difference in the locations. Quantify that and quantify how much variability there is within a group. Because here's two possible scenarios. Both for a gene, and in both cases I'm going to draw it so that the means are the same. Mean, 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 mean. Those means differ. They're not all lined up right next to each other. And because of the relatively small variation within the classes, it's pretty convincing that those differ. As opposed to a different scenario with the same means, but a lot more variability. In this case, because of the large amounts of overlap between the boxes, even though these distances, these centers are in the same place, the variation between the groups is still the same. The within group variation is much bigger, so it's less convincing. A p-value would be an Anova p-value would be small here, and it would be large here. And that's kind of what we would like to do in our case with the con data. Gene X, is it informative or not? Well, does its mean differ significantly between classes? A natural way to quantify that then would basically be to do Anova. And what Anova does is compute an F statistic that is, roughly speaking, between group variability, like how different are the means from each other across the groups, divided by an estimate of within group variability. So if the means are very different, but there's a lot of variability, the boxes themselves are very tall, you still won't get a very big F statistic. All that to say, this is why I used an F statistic here. So this is a manual calculation, an efficient calculation. You guys know from homework that scoring your genes in cross-validation can take a lot of time, computational time. Here's a function that will compute an F statistic for all 2,308 genes in one fell swoop using matrix operations. So much, much faster than a for loop. Okay, let me just run this. I don't know if this is going to have time to run, but I'll fire it off and say one thing real quick about this loop, and then we'll quit. So in the loop, we are going to do feature selection. Feature selection is a tuning process. How many features should you select? Like how much shrinkage should you do? How many neighbors should you use in K and N? We're going to tune, so we're going to use cross-validation. Within each cross-validation fold, we need to consider all the possible tuning values. In this case, all the possible feature set sizes that we want to consider. So I chose this as the collection of feature set sizes to consider. F sizes, I'm going to try the top 2 genes, the top 3 genes, top 4 genes, top 30 genes, and then from there let's go 40, 50, 60, all the way up to 2,300. For each one of those, so here's a loop over the cross-validation 5 folds. Inside there, I need to divvy up my data based on the fold breakdown, testing and training. Then I need to score the features, and that needs to happen inside the cross-validation loop for the reasons that we talked about in a previous lecture. So computing the F statistics, sorting the genes in terms of their F statistic, so from least to greatest, order them, greatest to least, order them in discriminatory information. And then for each of the feature set sizes we're going to consider, build the model and record its accuracy. So for each of 5 folds, we are going to have a collection of accuracies corresponding to the different feature set sizes. I'm storing all of this in a matrix. We're going to have all the feature set sizes in the rows and the 5 CV folds in the columns. Then if we compute row averages, that'll be averaging over the CV folds, we will have a separate single number for estimated accuracy for each of the feature set sizes. And we used CV cross-validation to estimate it, so these are reliable estimates. We can look at that, the accuracies, to pick, down here, to pick the feature set size that brought the best performance. So let's go ahead and make the picture and quit. There's the picture. Feature set size on the horizontal axis, starting at 2, way down here at 2. Then we tried 3, 4, 5, up to 30, 40, 50, 60, all the way up to 2300 out here. And this is actually a common shape for a picture like this. Bias-Variance Tradeoff. Increasing the feature set size increases the flexibility of the model. It also, to an extent, increases accuracy. But beyond a certain point, adding more features actually hurts. Because, like in your homework, some of the features are irrelevant. They're just noise. They're just going to add noise to your model. Feature selection process then is, where's the happy medium? In this case, most of the action happens for low numbers of feature sets, or low numbers of features. So I made a picture that zoomed in on the first 29, or the first so many feature set sizes. Same picture as the previous one, it's just zoomed in on the very left side. From this picture, you can achieve approximately very high accuracy, greater than 95%, according to cross-validation, using as few as whatever that is, 12 features. So as far as I'm concerned, that looks pretty accurate. 12 features is a very reasonable number. Seems reasonable that somebody would be able to develop a cheap, rapid assay for just 12 genes, if you just needed the expression level for 12 genes. Or this might be genotype for SNPs. Instead of the 500,000 SNPs we started with, if I can select 12, chances are we could turn that into an actual diagnostic tool. All right, I will quit there. Questions about that? Would you like me to finish going through, say, the random forest and tree stuff next time? Yeah? Won't take very long. So I'll finish the conscript going through tree stuff next time, and then we'll start with proteomics. All right. Okay.
You said for me that we didn't have time to run the code. Starting 3 o'clock.
Maybe take a screenshot. Maybe take a screenshot of your R console. I ran out of time. Here's my code. Here's my thinking behind my code. Here's a screenshot of R. I was trying to run it, ran out of time.
You won't be able to answer each of it either.
Yes, how are you gonna answer the rest of the questions?
I just copy paste the code.
Do you want us to borrow a matrix from somebody who did it? We say, I didn't finish it, this is my code for what I did, this is my buddy's matrix that he created, I'm gonna do the rest of it.
Well, frankly, as far as I'm concerned, as long as you worked hard at the exercise and learned something from doing it, like I hope that by doing this, you next time would, it'd be easier to get in there and code up something to do, even if it was hard and didn't have time to run. So if it was well thought out code and it didn't have time to run, even if that means you couldn't finish the rest of the assignment, I'm okay with that for the purposes of a grade. So just do the best you can, submit it, document what you did, and I'll work with Yabu to not hammer people on grades on it.
The rest is easy. Once you know.
Yeah. So it shouldn't be a big penalty if you weren't able to answer those just because of computation. That would be fine. I have given some people, a few individuals, permission to have an extra day because they had travel or one thing or another. So if you would like, I'll make that a standing offer. If you would like a little more time to work on it, if you email it to Yabu and CC me before Wednesday's lecture, because in Wednesday's lecture I'd like to be able to post the solutions. So that's fine with me.
So you don't include proteomics in
If I include anything about proteomics in the final exam, it'll be not R based, no coding. It would be a conceptual question. Like with proteomics, you don't actually, with mass spec proteomics, you don't actually get numbers on proteins, you get numbers on peptides. So tell me about the issue of rolling up peptides to proteins, in just a sentence or two. So the exam will be on your system. I posted on eCampus that I think that we can have this room 30 minutes early. Nobody's in here. So I'll be here 30 minutes early at the exam, and you can have that time. If you can be here 30 minutes early, you can have the extra 30 minutes. But yeah, it'll be the same. Otherwise, need R. I'll post the data sets that are required beforehand so you could download them and bring them with you. You can have any notes you want. All right, thanks. Technically, I'd like it to be comprehensive, but I'm going to strongly emphasize new material. But I would like to be able to ask, while you have these data open, tell me about the principal components, for example. Okay, thanks.